it's about 10 after, so we should probably get started, just keeping on time. So I'm happy to welcome Rich Townsend from Madison, where he's been for almost seven years. So prior to that, he did his PhD at University College in London, and then went off and, interesting side note, sidebar, he ended up teaching in Ghana for a year and working for Reuters, but then decided that the calling of astronomy was too strong, so ended up back doing research at University College London, and then went over the ocean to Delaware, where he was for a number of years doing research, before moving to Madison. So in addition to this research that he's going to be talking about, he does do other things, but I got a preview of his next slide, so I won't say anything else. But thank you very much.
Okay, thanks for that nice introduction, Kevin. So today I'm going to be talking about magnetic massive stars. I realize for you lot the title's probably a little underwhelming in the sense that I've used the word distant, yet I'm going to be talking about stars that you can see with the naked eye. And for you, that's not distant, that's absurdly close. Nevertheless, these stars are at least distant by terrestrial standards, and we're trying to find things on these stars and around these stars that are pretty elusive. That's my phone, which I'm turning it off now. Finding magnetospheres around these stars is a tricky process, and that's why it's kind of like ghost hunting. It's trying to find something that might not be there, shouldn't really be there, but, well, I guess unlike ghosts, these actually are there. What I do when I'm not looking for magnetospheres around massive stars is work on a couple of open source codes, one called MESA, which is an open source stellar evolution code, which is rewriting the way the global astrophysics community actually studies the structure and evolution of stars. It's a very big project. Some of you may have heard of it. It's a piece of software originally developed at UC Santa Barbara, now supported by many different people around the world. It has around 800 users. The paper describing it was one of the 25 most cited papers of 2011. And it continues to grow as a code. It can simulate the structure and evolution of anything from a gas giant through to a supermassive dark star. I also work on Gyre, which is a code for calculating the oscillation frequencies of stellar models produced by MESA and other evolution codes. And this is for performing astroseismology. If you're studying planets, those planets often go around stars. And to find out the age of a star the planet is going around, astroseismology is the best way to do that. And finally, I also work on looking at how we can use graphics processing units, GPUs, to accelerate the synthesis of spectra for stars that aren't just plain spherically symmetric balls of gas. This is an example of a contact binary, and this is colored according to surface brightness, and here's the light curve for the star, so I'm doing this with one of my students. So I have interests outside magnetospheres, and if you want to talk to me about any of these, learn a bit more about them, I'm around till Saturday. With that said, let me now talk about what I will be talking about. So some massive stars, and by massive star I mean anything with a mass above about 2 or 3 solar masses. So this is something that on the main sequence will have a spectral type O or B, a surface temperature above about 10,000 Kelvin. So some of these massive stars have magnetic fields, and these are strong magnetic fields, typical surface strengths of the order of a kilogauss. They're ordered fields, so unlike the sun's field, these fields are predominantly dipolar, and these fields are stable. We've been observing them for about 30 years now, and as far as we can tell, the fields don't change over time. So unlike the sun, they don't seem to show magnetic activity cycles. Now, we don't know where these fields come from. Massive stars, again, unlike the sun, have radiative envelopes rather than convective envelopes. So there's no sort of dynamo process in the outer layers of the star that we can use to generate a field. Likewise, we don't know where these fields come from. We don't know where they go. At the end of a massive star's life, if it's above about 9 solar masses, it'll undergo core collapse and form a neutron star. If the star happens to be magnetic when it undergoes collapse, then this field potentially could get frozen into the neutron star. And in fact, these objects may be the progenitors of really interesting compact objects like magnetars. Now, all massive stars have strong radiation-driven winds with masses up to around 10 to the minus 5 or 10 to the minus 6 solar masses a year. That's about 8 orders of magnitude or more stronger than the sun's wind. And these winds are highly ionized because the stars are hot. And so when we have an ionized fluid with a magnetic field going through it, we tend to get flux freezing, and the magnetic field and the fluid are forced to move together. And so the interaction between the wind and the field can potentially lead to interesting circumstellar structures that we call magnetospheres. A magnetosphere is just a region of space where the dynamics of plasma is controlled by a magnetic field. So that's what I'm going to talk about today, these circumstellar magnetospheres around massive stars. I'm going to start out by explaining how we actually go about detecting fields in massive stars. Then how we can reconstruct the magnetosphere that the field will sculpt as it interacts with the wind. Then I'm going to cover 3 specific cases of massive stars, some of which you can actually see with the naked eye, although not from Toronto, as it's been pointed out to me. And I'm going to finish up by talking about magnetic braking in one of these stars. This is the first direct detection of magnetic braking in a main sequence star. And when I say direct, I mean we've actually measured the rotation period of the star and found it's getting slower over time. So although in low-mass stars we know magnetic braking occurs on statistical grounds, if we observe old clusters we see slow rotation versus faster rotation in young clusters. This is where we've looked at a single object and actually directly measured the magnetic braking. So, measuring massive star fields, the standard way in astronomy we measure a magnetic field is using the Zeeman effect. So here's a nice picture of Peter Zeeman when he was a young man. And he pointed out that if we put an atom in a magnetic field, its energy levels get split, and moreover, transitions between those energy levels, the spectral lines arising from those transitions get split also, but not only split, but moreover polarized. So the Zeeman splitting arising from a magnetic field can easily be observed in the sun. If we take a spectrum across a sunspot, for instance, we can see that the spectral lines are split where the slit lies over the sunspot. For other types of star, we can directly detect the magnetic field via the Zeeman splitting. But for massive stars, the rotational broadening of the spectral lines is much larger than the typical Zeeman splitting. So we can't actually measure the splitting due to a magnetic field. But what we can do is measure the circular polarization that arises from the magnetic field. And we do this using a technique called spectropolarimetry. This is the Espedon's spectropolarimeter, which is on the CFHT 3.6 meter telescope, which I'm sure you're all familiar with, it being a Canadian facility. Espedon's allows us to take very, very high signal-to-noise, very high-resolution spectra of stars in both left and right circularly polarized light. So this is what a typical circular polarization spectrum looks like. This is the actual intensity profile. This is not a model. This is real data. The signal-to-noise in this profile is on the order of a few thousand. Okay? So you can see there aren't really many spectral lines there. This is a massive star, so they're relatively devoid of spectral lines. So typically what we do is we combine multiple spectra to get multiple line profiles together to try and enhance our signal to noise. This is the circular polarization signature, and this is the classical sort of sigmoid shape of a dipole magnetic field. And then this is what we call a null polarization spectrum. It just checks that we haven't goofed up our analysis. It should be 0. It is 0. And in fact, this is a spectrum for a B0.5 star that has a 130 Gauss field. Okay? So, using Espedon's and a number of other facilities, the Narval spectropolarimeter at the Telescope Bernard-Liot, which is in the French Pyrenees. It's a clone of Espedon. A group of us, about 60 investigators, spread around the world, and led by Greg Wade, who's at the Royal Military College just down the road in Kingston, we all got together and created a CFHT large program aimed at doing a systematic survey of magnetic fields in massive stars. As I mentioned earlier, we've known about these fields, at least in a few stars, since the 1970s. And a lot of that early work was pioneered in part by people at Canada, people like Tom Bolton. However, nobody had ever done a systematic survey of magnetism in massive stars, so this was the first attempt at doing it. And the MIMES project, which is an acronym standing for Magnetism in Massive Stars, was awarded, I think, 600 hours at the CFHT plus additional time at other telescopes to take spectra of lots of massive stars and look for magnetic fields. So these are the details of the observing program, and generally the results were this. Of all the stars surveyed, 545, about 10%, 67, show evidence of magnetic fields. Of those, about half were new detections, and about half repeat confirmations. I cannot explain why these numbers don't add up to 67, but there's obviously more subtlety to it than I'm aware of. I'm sure the observers could explain. I'm not one of the observers. So this is a breakdown of the distribution of magnetic stars as a function of spectral type. So the yes, the histogram shows you the gray histogram shows you the observed sample. The red histogram shows you the detections, and then the blue line shows the incidence fraction. And I think the scales are almost the same. The right scale is for the incidence fraction. So actually, no, they're both the same scale on both sides. Yeah. About 10% of these stars are magnetic. The fields typically range between 100 Gauss and 10 kilogauss, and quite puzzlingly, there is no obvious correlation on any of the stellar parameters.
How does this rate compare to low mass main sequence stars?
It's much less than low mass main sequence stars. Stars like the Sun all have magnetic fields, essentially. So this is a much lower fraction, but it's a lot more than 0, which is what we expect on theoretical grounds for these stars to have.
And sort of trying to look at the numbers here, would you say that 10% is consistent over a range of spectral types?
Yeah, I mean, this curve is essentially flat, at least within the uncertainties. So there's no obvious dependence on spectral type, there's no obvious dependence on rotation rate, whether there's pulsations present or not. The arguments that these fields are generated by a dynamo process are difficult to support if that dynamo process isn't correlated with any other properties of the stars. So at the moment, the origin of the fields is still a mystery, but we think that the fields may be remnants of fossil fields that were threading the protostellar nebula that somehow were swept up during the collapse of the nebula to form the star and didn't get shredded in the process. Hilding. There are some models that have been advanced that if the protostellar field is too weak, it does get shredded by instabilities. But these are the stars that somehow have had a field that's strong enough to survive that shredding process. Okay?
Are these magnetic stars related to the peculiar?
They are, in a sense, did you say BP? Yeah, these include the chemically peculiar BP stars. All of the BP stars are part of this sample, okay? So the BP stars, they're the ones that have been known about since the 70s, but the survey has extended the spectral types to much earlier types, so O stars as well. And the O stars don't show the same chemical abundance anomalies that the BP stars show. So basically, these stars down here are the BP stars, and then towards earlier types, these are stars that aren't obviously chemically peculiar, but nevertheless show magnetic fields.
So just while you're on this, can I ask what is your selection criteria? Because some of these were already known.
That's a very good question. The selection criterion is quite complex because on the one hand, to some extent, we're magnitude limited, but we're also limited there's a correlation between magnitude limits and how rapidly the star is spinning. because if the star's spinning very rapidly, we get very broad line profiles, and it becomes more difficult to detect the circular polarization signature, meaning that we have to go for longer exposures, but then you're subject to phase smearing, because these magnetic field signatures change over a rotation cycle. Depending on where in the cycle you observe the star, you're going to get a different circular polarization signature. So there's actually quite a messy selection criterion that's fully laid out in a forthcoming mega paper that's going to be describing the full survey. But it's by no means, you shouldn't regard this as an especially clean sample. Okay? Okay, so the magnetic fields that we observe on these stars, in some cases, channel and confine the star's radiation-driven winds and form these circumstellar magnetospheres. Now, and we know these magnetospheres are there because we can observe the light that they produce. For instance, in H-alpha emission, we can observe radio emission from the magnetospheres, and we can also see when parts of the magnetosphere are sitting in front of the star and blocking off some of the light from the star. So in order to build up a picture for what the distribution of matter is in these magnetospheres and find out how it behaves, we need to start off first by understanding what the distribution of magnetic flux is across the stellar surface. And to do that, we use a technique called magnetic Doppler imaging. So if we're able to get a time series of spectropolarimetric observations, we can actually build up a map of what the magnetic field strength is across the stellar surface. And not only the strength, but if we're able to get linear polarization signatures, we can also work out the orientation of the field. So these are some examples of magnetic Doppler imaging applied to a star, HD 37776. It's in Orion. It's just above the left-hand star of Orion's belt. It's also known as Landstreet star, after John Landstreet, because he was the first person to discover it. And it's kind of interesting, because rather than having a purely dipolar field, it's actually got a field that's dominated by a quadrupolar component. This is what the longitudinal magnetic field strength looks like. So this is basically the disk-averaged field strength pointing towards the observer. So this is what we could do back in the 70s via photopolarimetry, is basically get a sort of disk average field strength. This is pre-magnetic Doppler imaging. But now we have these wonderful circular polarization spectra. We're able to actually reconstruct the full magnetic topology across the stellar surface. So this is what the star's surface field strength looks like, and these plots show the orientation of the field.
So you have to assume the solid body was made up?
Yes. We don't ab initio, but nobody's ever found any evidence that there's differential rotation, at least from equator to pole, in these stars. The abundance patterns on the surface remain stable over decades, thousands of rotation cycles. And if you had differential rotation, you wouldn't be able to.
Like the sun, for example, would look
No, the sun is certainly very different, but for massive stars, all the available evidence, or rather there's no available evidence that there's differential rotation from a pole to equator. There's certainly radial differential rotation from the surface to the center. But we believe that, and in fact theoretical models suggest that strong anisotropic turbulence will tend to distribute angular momentum efficiently in horizontal direction. So basically we end up with a cellular rotation model where each at any given radius, the star rotates solidly.
I think there's a theorem that you're working on cylinders.
Well, that's the Taylor-Proudman theorem, isn't it? Yeah, that doesn't apply in this case. I think maybe due to the nature of the turbulence. Okay. Okay, so if we've managed to develop, if we've managed to develop one of these surface field maps, a standard approach is to characterize the field in terms of just a spherical harmonic decomposition. There's no physics in this whatsoever. It's just math, really. The field across the surface can be represented as a poloidal spherical harmonic contribution plus a toroidal contribution. And for HD 37776, the strength of the various spherical harmonic components look kind of like this. So in fact, I said this field was predominantly quadrupolar. Well, I was wrong. It's more like it's octopolar, since the strongest contribution is actually from an L equals 3 spherical harmonic. We'll come back to this surface field characterization issue in just a moment when we talk about, in fact, we'll come back to it right now, when we talk about how we actually reconstruct these circumstellar magnetic fields. So we know the field on the surface, but if we're wanting to develop a model for the magnetosphere and how the magnetic field interacts with the wind, we're going to need to know the field around the star. And to do this, we go through a sort of field reconstruction procedure where we take the surface field and we extrapolate it out away from the star. Now, as part of this process, we've got to consider the physics of how the wind and the magnetic field interact. And broadly speaking, the interaction is different whether we're inside the Alfvén radius or outside the Alfvén radius. So the Alfvén radius is depends on the magnetic field strength and the wind density. It's the radius where the wind speed equals the Alfvén speed, and inside the Alfvén radius, the wind is dominated by the magnetic field. Basically, the magnetic field behaves nearly rigidly, and the wind is forced to follow field lines. Conversely, outside the Alfvén radius, the situation is flipped. The magnetic field is kind of floppy, like sort of overcooked pasta, so English pasta. And the wind stretches the magnetic field out typically into a radial configuration. And for a dipole magnetic field, we can express the Alfvén radius as a function of the stellar radius, and using this expression here, where this includes something we call the magnetic confinement parameter. This was originally introduced by Staniwoki and Asif Abdullah, and it characterizes the ratio of the magnetic and wind kinetic energy densities back at the stellar surface. And so it tells us basically whether we're going to have a star with an Alfvén radius that goes far out, or whether we're going to have a star that has one close in. So for a star to have a magnetosphere at all, basically we're going to want eta star to be much greater than 1. If it becomes close to 1 or less than 1, the Alfvén radius is at the stellar surface, and there's basically no room for the magnetic field to channel and confine the wind. Hilding?
What happens in the case of rotation? Is rotation just going to be buried in the eta parameter, or does
This is for a non-rotating star. With rotation, you need to modify it to add a sort of extra centrifugal term. But that's something that can be done relatively. I mean, that was done in a 2007 or 2008 paper by Stan and Asif. It pulls it further in because you're with the rotation, the field lines open up earlier because there's extra stress on them. Okay, so for stars that have eta star very much greater than 1. The Alfvén radius is, so this is very strong magnetic fields and a relatively weak wind. The Alfvén radius is going to be located quite far from the star. And at least for the neighborhood of the star, the field is going to behave essentially as if it were force-free. So a force-free field is one in which the Lorentz force, or rather the individual magnetic pressure and magnetic tension making up the Lorentz force, are much, much stronger than the inertial terms in the hydrodynamical or the MHD momentum equation. And for a force-free field, the current ends up being, in order to satisfy the momentum equation, the current ends up being parallel to the field. So we can always write that the current density is equal to some constant of proportionality times the field vector. Given that the current, at least in the ideal in the fully conducting limit, given that the current is given by curl B, we can see that the dot product between B and the gradient of this constant of proportionality must be 0. So this means that there are essentially 3 types of force-free field. Ones where alpha is constant along each individual field line, ones where alpha is constant globally, and then in the simplest case where we have alpha 0 globally. So this is what we call a current-free field. which is also a potential field. It's a field where the magnetic field vector can be derived from the gradient of a scalar potential. So it's kind of analogous to electrostatics. So I'm going to talk mainly about these current-free fields. The situation's probably somewhat more complicated than that, but that's a good starting place. It's certainly how pictures of the sun's magnetosphere were first put together. Initial attempts at modeling the solar magnetosphere were based on these current-free potential field models. So potential fields, because the divergence of B is 0 and the curl of B is 0, the potential satisfies Laplace's equation. Here's an expression for the potential. This is just a solution to Laplace's equation in spherical coordinates. And we can apply some boundary conditions to determine what these expansion coefficients are in terms of the radial component of the magnetic field at the stellar surface. Now, that's something that we've measured from the magnetic Doppler imaging observations. So in principle, using magnetic Doppler imaging, we can find the potential that will produce the right radial magnetic field at the stellar surface, and then we can use that same potential to model the field everywhere. And this is how potential field extrapolation processes work. Basically, we get a potential that gets the radial field right at the stellar surface, and then we use that same potential to extrapolate the field throughout the whole circumstellar environment. So this is an example of, I think, HD 37776 Land Street star that I showed you previously. At the moment, we just have the star. The surface is colored according to the radial field strength. If I start the movie, this shows you what the magnetic field looks like across the stellar surface. In a moment, you'll see the magnetic field being extrapolated out from the surface. So to do this extrapolation, I know what the potential is at each point in space. I take the gradient of the potential, and that tells me what my magnetic vector is, and I just integrate lines that are tangent to that vector everywhere. So you can see that this star certainly has quite a non-dipolar field. It's a pretty complex field. Okay, so using this potential extrapolation approach, we can figure out what the magnetic field is around the star. Now we've got to work out, well, what's the distribution of material going to be on that magnetic field? So when a star is launching wind off its surface and it's launching that wind onto closed magnetic field lines, the wind is going to be forced to collide with itself. If we have a single magnetic loop, there are wind streams coming up from each foot point. Those streams are going to collide at the top, and they're going to shock. And then the post-shock material, it's initially going to be very hot. It will emit in X-rays. A lot of these magnetic stars are strong X-ray sources. As that material, however, cools down, it's eventually going to get back to a temperature close to the photospheric temperature of the star. If the star's not rotating, it's going to eventually fall back down to the surface. It can't balance on the top of a magnetic loop forever, because that's a point of unstable equilibrium. However, if the star's rotating, then the centrifugal force that comes from enforced co-rotation is going to hold that cool post-shock material up and support it against the inward pull of gravity. And material is actually going to begin to accumulate in the circumstellar environment, supported by the centrifugal force. Now, that material won't really be moving around at all. So it's going to be stationary. And we can actually calculate the distribution of the material by assuming it's in magnetohydrostatic equilibrium. So it's forced to, material on a given field line is forced to stay on that field line, and the only forces it's subject to are pressure and the projection of the gravity and the centrifugal force along the field line. The component of the centrifugal force and gravity perpendicular to the field line and the Coriolis force are all balanced by magnetic tension. So if we assume that the post-shock material, after it's cooled down, settles into isothermal magnetohydrostatic equilibrium, then we calculate the density along any field line, and S is just some sort of arc parameter measuring the distance along the field line. The density is given by some normalizing density times an exponential term, which depends on the effective potential. The effective potential is just the gravitational plus centrifugal potential. And this is something that we can trivially calculate. The only thing that's somewhat tricky is finding out what this normalizing density is, but we have a recipe for how much mass is being fed onto any given field line at any instant. And we can use that recipe to figure out what the normalizing density is.
So you're not solving like a Grad-Shafranov type equation here. You're just loading each field line that you've computed from your potential.
We're loading each field line with mass. And the great thing about this is that each field line can be done completely independently of the others.
Free, you don't need
Yeah, that's right. So this approach is known as the rigidly rotating magnetosphere model. And the first computer simulations of it were done in a crazy 10-hour road trip to Toronto back in 2005. It was the only other time I visited here. And I was running simulations on my laptop in the back of the car while this nutcase German postdoc was driving. It's not that he was German, it's just that he thought he was driving on the Autobahn. And it was an interesting trip. But the thing is, this is a model that can give us a three-dimensional plasma distribution, and yet you can run it on a laptop, so it's a really neat model. Just armed with the magnetic topology, you can work out what the relative distribution of material throughout the whole magnetosphere is going to be. I'm going to show you some examples now of applying this rigidly rotating magnetosphere model to a couple of well-known magnetic massive stars. Sigma Ori E is perhaps the most famous star. So to give you a bit of orientation, does anybody recognize this little splodge here? It's the Horsehead Nebula. Okay, so it's turned on its side. So actually, Orion's belt runs like this, and this is the left-hand star of Orion's belt, assuming we're in the northern hemisphere, which last time I looked outside we were. So this is Alnitak, Zeta Ori. This is the Horsehead Nebula. Now, just here, there's a sort of brightish star. This is actually the Sigma Ori system. It's a hierarchical system. The brightest dot here is Sigma Ori AB, a colliding wind binary, and that's the source of the ionizing radiation that lights up the Horsehead Nebula. However, off to one side is Sigma Ori E, which is in fact, it was the first B-type star that had a magnetic field detected in it. It was discovered by John Landstreet in 1977. But it was already known before then to be a rather weird star. It shows twin-peaked H-alpha emission and a double eclipse light curve. Both of these arise from the magnetosphere. But when the star was originally observed, before the field was detected, it was a bit of a puzzle. Based on this light curve, people thought it was an eclipsing binary at first. The period of the star is about 1.2 days, so it is rotating quite rapidly. These are the original magnetic field data fit with a sinusoid. This is the longitudinal field, so a sinusoidal longitudinal field comes from an oblique dipole rotator, basically a star with a dipole field that's tilted with respect to the rotation axis. Applying the rigidly rotating magnetosphere model to this star leads to a mass distribution that takes the form of a kind of a warped disk that has most material concentrated into two clouds that are situated at the intersections between magnetic and rotational equators. So this is the original model I came up with when on that road trip up to Toronto. This is just a sort of visualization. The mottling on the stellar surface is just a cheesy little aftertouch. It's actually the solar granulation pattern with a different color map. And I just did that because a blue sphere just looks boring. But don't think that's in any way real. The star has a magnetic field tilted at 55 degrees to the rotation axis. And in fact, we've offset the magnetic field from the center of the star slightly to try and explain asymmetries in the light curve and the H-alpha emission that we observe. So this is what the predicted light curve looks like, and you can see that we get dips in the brightness when material in the magnetosphere passes in front of the star. The minima are different because of this dipole offset, and likewise, this is what the H-alpha spectrum looks like. We see twin-peaked emission, and we see that the strength of the emission peaks, well, you'll see it in a moment when the bigger peak comes into view. On the blue side, it's quite a bit stronger than the red side. So how does this compare to observations? Does a pretty good job. I always overshoot this slide. Okay, this is a dynamical H-alpha spectrum. So basically, a color map showing the amount of H-alpha emission as a function of velocity with respect to line center and as a function of rotation phase. This shows a very, very nice double S-wave pattern. Basically, we got 2 emission peaks, and they're going backwards and forwards on that 1.2-day period. As they cross line center, we actually get little absorption dips. And this is the prediction of the rigidly rotating magnetosphere model. And it's actually a pretty good match. We see a sort of a double S-wave pattern. We see these absorption troughs as the material passes in front of the star. And what's most encouraging is that we see that the peaks on the blue side are strongest, and they alternate in strength: strong, weak, strong, weak, strong, weak, strong, weak. So it all looks pretty good. This is something that we did in 2005, and since then, this actually predates the MIME survey that got fresh data of this star. Since then, we...
What's the M dot profile on the surface of the star?
The M dot.
Yeah, do you assume you have a homogeneous M dot everywhere?
No, the mass loss rate depends on the orientation of the field at the surface. As the field goes away from vertical and towards horizontal, the wind gets choked off.
How did you determine the local M dot?
We take a parameterization based on MHD simulations of radiation-driven winds with magnetic fields. So basically, the local mass loss rate scales as the mass loss rate along a given flux tube scales as the square of the cosine of the field orientation at the stellar surface. And that fits the observed behavior in MHD simulations pretty well.
And you set one global M dot.
There's one global M dot that's kind of determined from the overall parameters of the star using standard Cassar-Klein radiation-driven wind theory. But that is in some sense a free parameter because at least for lower mass stars, the standard mass loss rate scalings don't behave that well, at least in the weak wind limit.
And in the movie you showed there are 2 lobes.
Uh-huh.
I'm just curious what makes the position of the 2 lobes special.
Those lobes are at the intersection between magnetic and rotational equators. And it turns out that the field, well, I should have mentioned that to answer that question, one has to think about why there's a hole in the middle and why there's some minimum radius for the magnetosphere to exist. And the reason is if you're too close to the star, the centrifugal force is never strong enough to support you against gravity. The reason why we basically get those 2 density-enhanced clouds, which you can see here and here, is basically that the inner edge of the magnetosphere sort of cusps inwards there. It's due to the way the magnetic field lines thread through the combined gravitational and centrifugal potential. And these points are at the intersect. If I run it for half a phase, no, that's not how to do it. See if I can stop it like this. No, I can't. The clouds are basically at the intersection of the magnetic and rotational equatorial planes. So when it's at the sort of edge-on phase, you're looking down a line that passes through both planes, and therefore you're looking down through the clouds. So one of the things we wanted to do with the new data from the MIME survey is take improved field maps that didn't just assume a dipole field, but were actually based on the measured field, and repeat the whole procedure. This is what the measured field looks like. It's to the, if you squint your eye, it's essentially dipolar, but there are some important departures. And this is what the longitudinal field curves looks like, and it's definitely not dipolar. You can see that, for instance, this maximum is kind of cut off. So this is what the reconstructed magnetosphere looks like. This is using a slightly more up-to-date visualization code, but you can still see that the material is concentrated into 2 sort of clouds that are kind of in the same location. Now the big question is, how well does it match the observations now? and like all good science, the fit has only got worse. So with improved observational data, we now find that the model predicts the red peaks for the H-alpha emission should be stronger, whereas in fact, obviously, the observations still show the blue peaks are stronger. So this is one of those frustrating cases where an improvement in the observations actually highlights the flaws in the models. Of course, that's something we should be happy about. It's frustrating for me, but it shows that there's room for improvement in the models. And so at the moment, we're working on trying to figure out what the reason for these discrepancies are. It's not just the H-alpha that's now discrepant. It's also that the model now predicts that the secondary minimum is stronger in the light curve than the primary minimum, and that's contrary to observations. So it seems a promising line of inquiry that I'm following right now is the fact that because of the star's abundance in homogeneities, it tends to have helium enhancement and metal enhancement around the magnetic poles, and helium depletion and metal depletion around the magnetic equator. That's going to have an effect on the radiative driving of the wind, both due to differences in the UV flux coming off the surface, depending where you are, but also due to differences in the opacity of the material being driven by the radiation field. And so initial attempts at basically modulating the wind driving based on the surface abundance distribution have managed to flip things round again so that the H-alpha emission is stronger on the blue side than the red side. So that certainly is looking promising. Basically, what this modification does is it changes the distribution of mass in the magnetosphere so that one lobe is now more massive than the other lobe, and that gets us back into agreement with observations. So let me talk about a second star now. This is a star we've already encountered. This is Landstreet star with the complex octopolar field. This is exactly the same picture as before, except I've highlighted a different star. This is where Landstreet star is. So it turns out there are a lot of magnetic stars in Orion, and this isn't a coincidence. Orion is the closest OB association to the Earth. Magnetic fields in massive stars are hard to detect, so we're likely to find them wherever there are massive stars close by, in stars that are bright. So I think there are, at current count, maybe 7 or 8 or 9 magnetic massive stars in Orion. This is what the longitudinal field looks like. These are field maps of the star. They only cover the northern hemisphere because we never see the southern hemisphere of the star. That's why they kind of sort of peter out down here. And this is what the reconstructed magnetosphere looks like. So this is the same field reconstruction I showed you before in the movie where the field lines grow out, but now I've sort of populated it with plasma based on that same rigidly rotating magnetosphere model. And you can see the magnetosphere is a lot more complex. Rather than a sort of oblique disk, it's now more like this sort of corrugated sort of wavy ring, and it's pretty messy. And it leads to pretty messy H-alpha variability. This is the dynamical H-alpha spectrum as observed, and this is as predicted by the ARM model. So this is the same rigidly rotating magnetosphere model, but the A stands for arbitrary. The original RRM model was for a dipole field, whereas this is for arbitrary field topologies. You can see that we get these very narrow emission peaks that show a nice sort of S-wave-like behavior, and we see that in both model and observations. So at the qualitative level, we're getting things right, but obviously at the quantitative level, we're not getting the phasing of these blobs right. So there's clearly still something that's not quite right there. That's unsurprising because this star has a very complex field. What's less clear is whether the problem is in how we're extrapolating the field or how we're putting mass onto the field lines. We're not sure yet what's going on. So still much room for improvement, but at least a good qualitative start at modeling the star. Now let me go on to a third star. This star is Telesco. It's a strong X-ray emitter and a very slow rotator. It shows very narrow line profiles. It was the first star that had a field extrapolation performed for it. based on magnetic field maps that were done in 2006. And the star shows not only X-ray emission, but X-ray emission that's not phase modulated. So over one rotation cycle, there's not a statistical change in the strength of the X-ray emission. This is what the X-ray spectrum looks like. So it peaks around 1 keV. That's relatively hard for this sort of star. So these are what the, wow, that really is a crappy image, but these are what the original field extrapolations look like. These were done by Jean-François Donati. And the star has got a very non-dipolar field. These are what the field maps look like. And again, it doesn't look much like a dipole. You can actually see there are multiple polar spots on the star. So the way the field reconstruction was originally done for Telesco warrants a little bit of explanation, because this is a star for which the force-free approach is certainly wrong. The star doesn't have a particularly strong field, and it's got a moderately strong wind. So we expect the field lines to get seriously distorted and then pulled out and broken open by the wind quite close to the star. So obviously we can't use a potential field extrapolation approach for this star, but nevertheless we do, because we've got to do something. In fact, we're taking our lead from the solar physics community. The initial potential field models for the sun were modified to allow for open field regions by introducing something called a source surface. So basically, a source surface is a virtual sphere, and on that sphere you force the field to become completely radial. And this turns out to be achievable just by simply modifying the terms in the potential expansion that we do for a normal potential field extrapolation. And if we modify those terms, we can force all the field lines to become radial at some distance from the star, and then from that point outwards, we just extrapolate the fields outwards as radial lines. So the source surface approach was used in Telesco's case to basically artificially open up the field lines at some finite distance from the star to mimic the effect the wind would have on the magnetic field. And these movies here show an example of a field extrapolation for Telesco done with different choices of the source surface radius. So the source surface is actually shown as the sort of faint grey sphere. And you can see on this surface, all of the field lines become completely radial, and then outside that, we just extrapolate them out to infinity. So for a source surface close to the star, there are only a few closed field regions in the star's magnetosphere, and they typically don't extend very far from the star at all. But as we go to larger source surface radii, you can see we get much larger magnetic loops, and most of the magnetic field lines coming out of the stellar surface remain closed. And then this is an example where the star has no source surface, so all the field lines close at some finite distance from the star. So when the original analysis of Telesco was done, it was assumed that the source surface was at 2 stellar radii. So the magnetic loops are very, very small, and it's difficult to understand how, if X-rays are being produced on those magnetic loops by wind collision shocks, the wind streams colliding with themselves, it's difficult to understand how that X-ray emission wouldn't be rotationally modulated. Because remember, the observations show no rotational modulation. So this was a bit of a puzzle. So I've revisited this problem recently, and I discovered that the mass loss rate for Telesco, the published values in the literature, have a large enough spread that there's actually quite a lot of uncertainty in the location of the source surface. So this is a graph of the source surface radius as a function of mass loss rate in solar masses per year. And this is the range of mass loss rates that have been published for the star. So this is the mass loss rate that was assumed for that original reconstruction I showed you, and it gives us a source surface at a little over 2 stellar radii. But if we go down to a lower mass loss rate, then we get a source surface up around 4 or 5 stellar radii. For a source surface out there, we get quite a lot of closed magnetic loops that potentially could harbor X-ray emission that won't be rotationally modulated because it doesn't end up getting taken around the back of the star and blocked off by the star. So do we have a reason for believing that these closed loops do indeed extend out further? The star does indeed have a lower mass loss rate. Well, a careful reanalysis of Chandra observations using the line strength ratios of helium-like ions, shows that in fact the X-rays are consistent with a formation radius of 4 stellar radii or more. So it does indeed look like that the problem with the original Telesco field reconstructions was that the source surface was put too close to the star, and basically the magnetosphere was constrained to only have very, very small loops, whereas in fact the loops are somewhat bigger, consistent with a lower mass loss rate. So it looks as though the puzzle of Telesco has largely been solved. Let's get on to the final bit, magnetic braking in sigma ReE. So as I mentioned at the start of my talk, sigma ReE, the archetype magnetic massive star, has direct detections of its magnetic braking. The way we've done this is that, if you remember from the animations I showed you, the material in the magnetosphere passes in front of the star twice a rotation cycle. Now, the dips in brightness caused by this transiting material were first measured back in 1974. So potentially, by combining those old measurements with newer measurements of the timing of these dips, we can actually see whether the period of the star has been stable. And the way we do this is this will be familiar to people who've worked on binary systems. We construct an OC diagram. This basically compares the difference between the observed time of an event versus the calculated time of an event, assuming some sort of ephemeris. And if we assume a linear ephemeris, which basically says the star has a constant rotation period, then we're unable to fit all of the observational points. The dashed line shows you what happens if we assume a constant rotation period, and the dashed line does not go through all of the observed times of photometric minimum. Whereas if we assume a linearly increasing period corresponding to this parabolic line, it passes through the points perfectly. And it tells us that the star's rotation period is growing with time, with a characteristic spin down time. So this is sort of the E-folding time of the, or E-growing time of the rotation period, is around 1.3 million years. So this was the first ever direct detection of magnetic braking. The reason why we're pretty sure it's magnetic braking is that we've done MHD simulations of what the rate at which we expect the braking to take place. So the magnetic braking is occurring simply because as the wind flows outwards from the star, the magnetic field it's interacting with is acting as a lever arm and making the star very efficient at losing angular momentum. So we can calculate the rate of angular momentum loss, and we find that it follows a simple scaling law that depends on this magnetic confinement parameter. And if we plug in the confinement parameter for sigma ReE, which is of the order of 10 to the 5, we find a braking time scale of 1.4 million years. And that's very close to the measured time scale of 1.3 million years. In fact, so close that it looks almost like we fudged it. We didn't fudge it, but the fact that they're so close is more blind luck. I'm just happy that they're within the same order of magnitude. But it's just the icing on the cake that they're in fact that close. However, since the original result was published, I've gone out and with collaborators got more observations and added to the OC diagram. I had to exclude some of the data because all of the comparison stars got half a magnitude brighter. Well, not all of them. If all of them had got half a magnitude brighter, then it would have meant that my star had actually got half a magnitude dimmer. So what's the physics? I don't know. But I'm still trying to figure that out. The spin down is still present, which is encouraging. And we've got a revised estimate of the spin down time scale of a little bit shorter, in fact, of 1 megayear. So we're continuing to monitor this star and look for other stars that are showing evidence of magnetic braking. But I think this is my favorite result from all the work I've been doing on magnetic massive stars, because it really demonstrates how you can do some remarkably precise measurements with them, and how you can more generally just use them as really interesting laboratories for understanding the interaction between matter and magnetic fields. Regions of parameter space that you really can't achieve on Earth. The plasma beta parameter that we're working at for these stars is of the order of 10 to the minus 6. And that's not something I really think you can get down to in the lab. So these are really interesting objects. Next steps, look for better field extrapolation approaches, see what physics we're missing, and try and get some 3D MHD simulations running with the actual observed magnetic surface maps as the lower boundary conditions. But most importantly, keep up a very, very fruitful dialogue between observers, theorists, and modelers, and one that's, for me, been very exciting, especially because I've had I've had the privilege of interacting with a lot of very clever people from all of these different disciplines. Oh, that's my backup slides. I'll get to that if anybody asks the right questions. Okay, thank you very much.
Thank you very much. So we've had some questions already. Any follow-up questions at the end? Yeah.
Yeah. So in the movie, there is a hole, and you say
Uh-huh.
the hole exists because centrifugal force is not strong enough.
Sure.
So I'm just curious about the case in which all the closed magnetic fields are within the hole.
In that case, you won't actually get any you won't actually get any material stably supported. You won't. However, that said, for some stars, the mass loss rate is so large that you can get material that's just supported up there dynamically. It'll eventually fall down, but it stays up there for long enough that there is actually an observational signature.
What do you mean by dynamic?
So, like balancing a pencil on its tip. We know it's going to fall over, but it remains there for maybe a few seconds before it does.
Yeah.
Okay, so even though the material is unstable, its residence time in the magnetosphere is long enough that it produces an observable signature.
So, yeah, what I'm thinking, the picture is that you have material coming off, short each other.
Mm-hmm.
Really, it's the X-ray, cools down and fall back, and you have new material coming off doing the same thing.
Mm-hmm.
That kind of process could happen along every closed magnetic field line. Do you think that would naturally explain why the X-ray flux does not show any rotational modulation? Because this kind of thing could happen everywhere.
So, I mean, we think indeed that sort of thing does happen everywhere. But at least for the B-type stars, there's never really enough material, or at least enough of the cool material for it to produce a signature at optical wavelengths. The wind is just too low density. The difference between this sort of transient distribution of material.
How do you know that the wind is too low density?
Because we can observe the wind density in ultraviolet resonance lines.
But you know, most of the material just falls back. It does not contribute to any, infinity wind. So most of the material just...
Well, no, sure, but we can still see the wind material coming off the... we know how much material is coming off the surface based on UV resonance lines.
Okay.
We know the rate at which it's coming off the surface. And when it falls back, I should add that it doesn't fall down because it's still ionized. It actually slides down to one foot point or the other, and then a new wind gets launched.
Okay. Yeah, let's talk about it.
Sure.
I don't understand it further.
Any other questions? Yes.
Quick question. So it's hard to measure the actual rate of spin down,
Uh-huh.
but are the rotation rates of magnetized stars slower than non-magnetized?
Yes and no. So at one end of the spectrum, there's a magnetic massive star with a rotation period of 55 years, claimed. I'm not sure I believe that, but there's because obviously it's difficult to observe a star for 55 years or more. More realistically, there's one with a very well-confirmed period of 500 days. So that's at the very slow rotation end. But at the fast rotation end, a couple of years ago, we discovered two stars with rotation periods of half a day. And these stars are within a hairbreadth of being rotating at the critical rotation rate. We do think magnetic braking does tend to lead to slowly rotating stars, but in some of these objects, they're just so young that they're still rotating very rapidly.